Well, good afternoon. I'm going to speak about partial actions. Firstly, I want to give you some motivation about this topic because it's not just pure generalization of what we know about actions of groups over sets, because there are plenty of examples about this. The first thing that it comes to my mind is that, for example, if we have something like a space where there's no entire symmetry in it, we know that we can build some operators inside them, like a half plane, you know, something like this. And well, I'm going to this and this, something like this. And as we've seen through the other courses, we know that if we have this type of space, we can push this space by some operator, like some shift, where we push this this space into, like, we take it and we move it upside, right? And this is an action of some monoid, not group, in this space. So we can build something like n, something like n acts in some way in this space. And what we know is that this is, we could maybe make it this as a group, but the problem is that we know that the inverse operator is something like push it down, but the problem is that it is not well defined in this section over here because it goes out of the space. Then here is where something like partial actions comes to help us, save us, in fact, where instead of maybe acting every element of this space or over all of this space, we make it act just in a portion of this space. So as an answer of this problem here, it will be that if n pushes n space this half plane up, then what we can do is just redefine the domain of the element minus n to make it go down. So instead of taking all the half plane, what we make is that minus n will act only in a section where this action will be well defined, and we have some reasonable properties. So that's what we have. We have then this action we represented by a function, which is called by theta, and this will be defined in some domain of theta n, and it will go to the image of this function. The same goes here. And as we are used to the space of partial bijection, so it is not hard to understand how we are going to compose, how we are going to operate these functions via composition, but via a composition with some things to fix. Then with this kind of motivation, I can give you the formal definition of this. And as we can see, we have a space. Something that I'm going to say you now is that we are not going to be interested in the topology of the space X. We're just working here as sets, and that's all. I think that work is going to be for Nestor, I think. the topological part, not mine.
And maybe you noticed even in the drawing, the drawing asks you for completing the drawing somehow. So you dispose only of half a plane, but you can imagine that if you complete with the lower part, this would be quite close to a usual group action. And of course, this could be random. It could come just from the very concrete situation. But one of the results would be that we can do such a thing in general. This means to complete somehow the space on which the group acts, such to transform this rather creepy, rather ill partial transformations into a full and honest group action. And this would be, in your case, the lower half plane, isn't it?
Yes. Yes, exactly. So if we have the entire group, we have a lot of more properties than just a monoid, as we can see later. Well, we have here, and as we can see in this part, we have a collection of subsets of X and a collection of functions, and this is the way they are going to work. And as you can see here, there is immediately a hidden property here, where if we take, instead of theta g, we take theta g minus 1, the inverse. That's a good thing that we have here. So this thing is going to start immediately in d sub g, and it goes to d sub g minus 1. So we have here immediately a nice property implicit here, where we can compose theta g with theta g minus 1. But this is not, we need another property if we are going to work with other elements of the group. Well, reasonable hypotheses, such as the one of this group is going to be the identity, and its domain is going to be the whole space. And the other one is going to be this one, which is very reasonable, because what it says is that composition works well with the operation of the group. And we have to understand here what this notation means. Means that what we have is that F is going to be a subset of G if domain of F is going to be contained in the domain of G. And also we have that if we restrict this function G over the domain of F, we're going to get exactly the function F. That's the thing that it's like when we worked with partial bijections in a set X.
I would like to ask you something. Maybe you recall we discussed partial actions of inverse semigroups. So even without writing down the exact definition, do you remember somehow, vaguely at least, what the definition was and how it is connected with this one? So an inverse semigroup is much more general than a group. We remember this.
When we have something like this, right?
Yes.
Some properties like this,
and a similar one for changing F into S minus 1. And we asked the unicity of this one. Anyhow, exactly. let me state a question. Is this more general? Because the object that it's acting, the inverse semigroup, is really much more general than a group. So you could ask, why do we reinvent things? Why do we look at this example, since we have seen something which seemed to be more general? And the fact is that it is not more general. There is a certain detail which shows that the two are incomparable in general.
Yes.
So do you remember what
For example,
what happened?
I remember that we had the need to define something like the vacuum function in partial
Yes, it is true.
bijections, and
Mhm.
but here we can't do the same. We don't need it, for example.
You don't need it, but let us say if I show me please, Diego, once again the definition, your actual definition.
Ah, that one?
That one. The difference is in the point two. So for an inverse semigroup, you have a larger class of objects acting, these inverse semigroups, which are more general than the groups. But you asked that the correspondence between G and theta G should be a precise morphism. This means you have equality here and you don't have inclusion. So there are two differences. One is putting the inverse semigroup actions at a larger scale because the object that is asking, that is acting is more general. But on the other hand, you ask something more precise for inverse semigroups. You ask equality here. And I'm almost sure that if you try to combine the two, it would be difficult. So here it is general because the composition G times H acts as an extension of the two other objects, G and H. But the group should be a group, which is quite precise. So there is no hierarchy, there is no inclusion between the two definitions.
Yes, I tried to make a relation, but I didn't figure it out, that thing. In fact,
this is what's happening. If you try to define inverse semigroup actions with inclusion, which would be very general, you would probably not succeed. So the theory of inverse semigroup actions need equality here and not just inclusion. And if you put inclusion, it is a nice situation to have a group acting. So finally, we will see at a certain stage that there are connections between the two theories, but that they are not direct somehow. So very often you will have such functions defined by a group, partial bijections, and to go to the inverse semigroup, if you want to do this, you will need to take the smallest inverse semigroup generated by the elements of the group. And you can do this in such a way to ensure equality afterwards for the resulting action. So this is a reason for which the connection is not very, very simple. And one category is not a subcategory of the others. The two types of actions are incomparable in general. This is what I wanted to say.
Okay. Well, if you're curious about when do we have something like this thing, it's not hard to see it. For example, in the example of the half plane, have something like this. I don't know, like this. Pop, pop, pop. And we can consider something like this. Then this must be a subset included in the theta 1, which is going to be the identity in the whole space. Then what we can do is to take a theta g minus 1, like the function that take one step the plane down. Then what we have is that the domain of this function is going to be, for example, this is x, like this type of, then the domain is going to be something of this way. And it goes to go to the whole space, half, let's call it h. And then what we have here is that this function here has a domain of this set, and then it's not going to be equally to the identity. They are going to be equal in the domain, but they are not going to be the same function. That's all. I don't know if there's any question about this.
I have a question. Like, if we start from the idea that you stated at first, like not the self itself, the definition, but like this action on this grid, um, it's not like from the beginning obvious that there is a group behind. If, as we know a little, we know that Z is hidden as a group here. But like if we are looking at the action, like what these things do, it's not obvious that we are dealing with a group a priori. But from the definition, we see that we're always studying a group. So my question is, in the actions that we will study, uh, will it will we always be able to find like the bigger group that we are thinking
Ah,
of?
I don't know. I'm not sure about it. Uh,
Well,
I
it
don't know if
depends
it
on,
were.
it
I
depends
think
on
it
your
just
starting point.
depends.
So most often, if you don't want to arrive in some nice way to the problem, you are given a full group acting in such a partial way. So this is a simple-minded answer. In practice, I guess that
I think it depends of the action.
it depends on the action. And anyhow, because n is a monoid generated by one element, and z is an element generated, once again, a group generated by one element, here actually you just need to give the first step. And for the first step is the function theta index 1, isn't it? And then you look at its inverse, just defined on the range on the first function. So let us say that the function is called phi. It is not theta index 1. You don't think that you would like to iterate it. This will come later. Well, you have a function which is everywhere defined in this case, but you are not obliged. And it goes to a range. It is not subjective. Then you define the inverse, defined only on the range and going back to the entire space. And then you iterate both of them, you would get a full group. So in this case, this is how you can see heuristically the way you arrive at a group. But strictly logically, what you need to have in the definition is a group obtained in some nice intuitive way, in some artificial way, acting in such a way by partial bijections, if this is an answer to what you asked.
Yeah, yeah.
Um, well, we have that. Another thing that we can see, let me see if I can find this here. Yes, maybe I was gonna show you some examples, but like with this example of the shift, I think that we're okay by now. Maybe later I'm going to show you some examples because we're going to see what does it mean, what it means to have two actions equivalent, and then we are going to need some other examples. Another thing that we have to at least see once is that when we have the composition here, for example, we have theta g composed with theta h, what is going to be the domain of this function? So we know that the domain of this function, for example, is going to be all x in x such that theta h of x is going to be in the domain of theta g, right? And then this means that this element is going to be here. But for x to be in theta h for the element theta h of x to be well defined, we need that x belongs to theta h minus 1. Then, let me see, before I screw it up. Yes, this part of here implies that x is going to be in the inverse image of theta x dg minus 1. And of course, as theta is well defined, then this is going to belong to this part. Then what we have here is that x is going to belong to this intersection of here. That's what I wanted to show you. We are going to need this in the next part to understand well why this happens. It's rather simple, in fact, but I wanted to show you.
I recall you that unbounded operators in, let's say, Banach spaces or Hilbert spaces also compose in this way, but you cannot do all the steps until the end, because in general, with two unbounded operators, which are usually defined only on smaller sets, let's say on dense vector subspaces, you are not sure that one of them or both of them are invertible. So you just have to stop the definition at the middle somehow. You say that the domain of S times T is a domain, the points in the domain of T, which is at the right, such that applying T, you arrive in the domain of S, and you cannot say anything more about this. But in your case, Diego, you succeeded to go on with the computation and to get a final closed form for the belonging of this point X, because theta H was action. So you can apply the inverse image, and it is a real inverse image. It is not just in the sense of set theory. It is the function theta minus 1 applied to something. So this is why your final formula is more precise than what you get for multiplication of unbounded operators.
Yes.
And I also recall you, be careful with inverse images of intersections. Usually they are not the intersections of the inverse images, but this happens if the function is injected. And now it is injected, it is even a bijection. Yes. So you can afford to write even more than this. This is also theta h minus 1 of dh intersected with theta h minus 1 of dg minus 1 in this case. But it is not true in general. Intersection behaves strange way with respect to inverse images. Okay.
Okay. Then, well, here is a nice image of this. That. And this is the formula. So we can see it right now. It's not that hard. We can, at least I like to paint this. This is going to here, and this is going here. I'm sorry, here. Up. There. And this is how the composition works. So we can see now by this draw that this is in the book that we have the composition is a subset of this other, and how the domains work.
And it is easy to see how you get a void domain.
Yes,
Just
yes.
It might happen that what you have in the middle do not intersect. DH might be disjoint from DG minus 1, and you already arrived at the void function, which is the composition of the two. This is not very bad, because the void function is always the restriction of anything, in particular restriction of theta indexed by h times g. So this happens easily to lose everything when composing functions.
Yes, this example will be like take the upper half of plane, I don't know, something like this, and take it a grid like this, and take a n to act in this space as a rotation. Then if we rotate this by pi, for example, this is going to be the domain, the rotation by pi, because draw it to something like this, right? And then if we compose this 2 times, then we have a trivial domain, because nothing can compose it in this space 2 times rotated by pi. Half pi, I'm sorry, half pi. Yes. Well, before we are going to work a bit more, we need to understand some little properties which it was hinted by Marius, which is this one about how the functions, these partial actions work. Where we can see that these definitions fix a lot our action. It's not, they don't have a lot of freedom to act. In fact, they get very restricted, in fact. So what we have is that the inverse of every action is going to be what we think, what we feel is going to be the action by the inverse element. And how do we prove this? Is by using the condition 2. Let's remember the condition 1 was that I don't know, yes, the domain of the neutral element is going to be the whole space, and that theta 1 is going to be the identity, and condition 2, it was all about composition. Then what do we have here? We have that to prove this, we need to inverse this one, and we can compose it by left with this one here. So this is going to be contained in the composition in the group, and this is going to be the identity in the space dg minus 1. This is not so hard to see because the domain of this function, as we've seen here, we can check it by this formula, for example. That's one way, but it's really easy to see that the domain of this composition is going to be dg minus 1. And then we have that this function here is going to be a left inverse of the function of the right. And then if we compose it by the other way, what we have is the same thing. And this is going to be the identity in dg.
Sorry, Diego, I'm not sure of your equality. I think that you should move this dg minus 1 to the left. Because at the right, if you want to describe...
yes, I'm sorry. Yes, you're right. Yes,
this is theta index 1. And this is the entire space.
Yes, that one. I'm sorry.
We agree, isn't it?
Yes. Because, of course, this is going to be theta 1, and that's the whole identity in the whole space. Yes. I got too excited. Yeah. Then we have this thing, which is going to be, again, useful in the future. And before this, what we are going to speak about a bit more is that if we take out this condition here, for example, these conditions, what I mean with this is that when we define we can do just something like this. X1 goes to Y1, where X1 and Y1 are going to be subsets of the whole space. If we define this as partial actions, if we want to have an equivalent definition as the first one, we're going to need to give more properties. It's not that easy to define this. We need to be more specific. There are more conditions which are hide here in the definition of partial action. That's why I spoke a lot about this secret property here, where it ensures us that the composition works.
Sorry,
Yes.
I have a question. Does it make sense somehow, like, to consider one of these subsets as an empty set? Are we considering that case?
In this book, no, but I think that it's worth considering, because there's a lot of cases, like the example that I showed before, where you have where you can't define the composition of two elements, but you know that it exists because you can compose by these definitions, and it's not at least in this section. Ruy doesn't speak about what happens if some of them are trivial, which of course they happen.
Some
but
of
huh?
which one should be trivial? The domains?
Yeah,
Yes.
Any domain is trivial.
It is
Yes.
possible.
Yes, it is possible.
One of the subsets of X is the void set.
Yes.
And you should consider that this is possible, because even if for a couple of elements G and H, the domains are not trivial, it might happen that the domain, you are right, this does not appear directly in. No, I think that this is possible. It's not said explicitly.
It is not said, but I think that it should be a little remark about it, because at least to me it sounds a bit strange that we can have something like this, right? This is the rotational pi, and you can define something like this because both of them are going to be trivial.
Well, you have to push somehow the definition to this absurd situation. So, for example, you imagine that composing the void function defined on the void set and having the void image, composing it with something is once again the void
yes, I'm a bit interested in this just because, for example, when we have to restrict the action on a subset, we want to have a subset, a sub-partial action, then the case of having trivial domains should be a lot more frequent. That's all my opinion about it. In fact, that's why I spoke it in that way.
Diego wants to say that even if you are lucky and your domains are not a priori void, because this is the situation you are given, later you will just take a quarter of the entire space and you would try to make a restriction to this one. And since some of the big domains which were already existing are disjoint, maybe it may happen, are disjoint of this quarter of your plane, you will get naturally by the restriction.
Professor, excuse me. Your microphone, or it's me?
My microphone.
He might have been covering.
So now is it okay?
Yeah.
Yes.
Okay.
And I was also thinking in the case that if we are like somehow forced in the opposite direction, like to consider a wider group or a wider domain for some reason, it might be reasonable to force like the definition so that in outside of some nice space that we already know, it might behave like in the empty way.
Yes. Yes, it's the same as restricting the set. If we make the group a lot bigger, or we have a bigger group and we have yes, I get it. I think the same.
But I think that in the extension problem, you keep the group and you make the space larger. I'm not absolutely sure, but the idea was not exactly to enlarge the group. You are misled somehow by the fact that in practice you see rather often the action of a sub-semigroup, as was n inside of Z in the first example. But actually what you had the Z action on something which was a half plane, and later you would like to dilate this, to extend this to the entire plane. So if I'm not wrong, what you want to extend is the space to make the same group act fully, globally, and not just by partial actions. But who knows, maybe you can also do what you want, also enlarging the group. It is possible and it might be useful sometimes.
Yes, just taking advantage of, nothing. Taking advantage of this part, I didn't speak about it, but if we have this thing, which is the, rather, we go back to the global actions of groups. It's what we are used to. And global dynamic system. Well, going forward, what I was speaking about is that it was having an equivalent definition of partial actions, where if we define them just like this thing, like we are used to in partial bijections, we're going to need a bit more specific if we want to get again a partial action, which is going to be shown in this proposition. And then what we do in this proposition is we use the first condition 1, which was, I'm going to call it I prime, I'm sorry, which was that D1 is going to be the whole space, theta 1 is going to be the identity in the whole space. If we take away the condition 2, which was this thing, and then if we take it away, we need to add these two conditions to get again a partial action. And this is going to be an equivalent definition, and it's going to be very useful in the next section at least. Okay, we can prove this. Sorry, looking for notes here. Yes. Okay, so if we remember, yes, if we remember, we're going from left to right. Yes, the domain of when we compose two functions. If you forgot what we are going to prove here, this is all in Ruy Exel book, so you can see the book in parallel. And then the domain of this function is going to be theta jk, I'm sorry, jk, k minus 1, tk, intersected with the j minus 1. And then, as we have this condition, jk, we have that jk minus 1, it's going to be included in jk. Let's remember, what we try to go here is that a condition between the composition function, the domain, and another domain here. And then what we are trying to see is that what are the relations that we have in the domain of the composition of two elements. So we here are using the condition 2 of partial actions. Then we have this relation here. This is because of there. Here. This is because of this condition. Now, why did I do it this way? Because now we can make this 2 to look like this 2 here. So what do I do is to make k equal to g minus 1 and j minus 1 equal to h. So what we have here is that we have g minus 1 d sub g minus 1 intersected with the h. It's going to be a subset of course, the gh. But as we've seen, this thing here is going to be equal to the theta g, so we have condition 1. GH. It's just playing with the definition. And now condition 2. Oop. Need to add another page to have some space. And condition 2, what we have to show is this thing here. I'm going to cut it, paste it. This is what we want to show. And then what we do, we take this element here. Then if we apply dh, because remember we had to apply theta h and theta g, then what we have that x is going to belong to and there, sorry, theta h is going to belong to theta h, the h minus 1 intersected with the this, and and then yes, we use condition 1, and remember that we have this djh minus 1 because of this condition here, this one. We can see that this is going to be inside of sorry, going to write it again. Use this relation that this one here, here, there. We have this condition, and what we do here is we take j equal to h, k equal to gh minus 1. Let's remember this condition here is just what happened when we try to compute the domain of the composition. Yes, I'm sorry. Let me see. Yes, that one. And when we do this change of variables, we have that theta. That's right. Oh, I put it the wrong way. We take j here, j minus 1, k. Here is JK. There. Then what we have theta H of the H minus 1 intersected with GH. That's going to be inside of the H times JH minus 1, and all of this is going to be equal to DJ. And DGJ minus 1 is minus 1 is not going here. There. What we prove is that theta H of X is going to belong to DG minus 1. That's all. And as we have this thing, this is looked a little tricky, but it's not. It's just working with the definition. And then what we have, remember, we wanted to show this type of composition when X belongs to this intersection. Then what we need to prove is that if X belongs to this set, then the image of X by theta H is going to belong to the domain of theta G. Then what we prove here is that theta H of X is going to belong to this, then X belongs to the composition, to the domain of the composition. Then what we have that as we have the condition 2, because we're working with a partial action, which means the thing is going to be included in this function here. Then what we have is that if we apply X inside this, as X belongs to this, to the domain, then this is going to be equal to dgh of X, which is what we needed to prove. Then here we have one direction. Yes. There. And to the other way is rather similar, but I think that we could skip it. But if you're interested, we can continue. In fact, I just try to prove the more natural part, but it's trickier or well.
This can be read from the text.
Yes, it's not hard. It's very easy. It's just, I think that the only thing that could be difficult here is that there's a lot of change of variables. In fact, sometimes Ruy says, well, let's change G by G minus 1, and the equation looks a bit confusing, but just step by step, it should work fine. And let's see. Yes, there are other properties like this one. And to prove this thing, what we use is what we have, in fact, that this condition here is a better version of the condition 1 of 2.5, which it was this one again.
Sorry, I interrupt you, Diego. So, well, nobody would remember the points 1 and 2 in this last proposition, but they are, after working with them a couple of times, they could be memorized on one hand, and on the other hand, although they are not very simple, you can look in the book or you note it on your on your piece of paper, and it is exactly what you have to check. If not, the initial definition was slightly nicer. It was easier to write it. It was just a inclusion of mappings. But when you have to check it in practice, you have to think about it. You have to recall what the domain of the composition is, to write it explicitly and to make the comparison. So this version you gave us in terms of the points 1 and 2 is more direct, even though it is not easier to remember than the definition.
Yes.
You know that this is what you have to check. You have domains, you have to know them in advance, and you make the that's all. Hello, what was his name? Its name? She's name?
No, they are speaking there.
The name is?
Paula. Paula. Yes. Well, someone was calling at the door. That's what happened. Yes, in fact, this definition, at least until what I read, they are very useful to work in proofs instead of explaining things. For example, this property here, the proposition 2.5, which is this one, is going to be very useful to prove this other part here. And it became very, very easy to prove, in fact, in rather 3 lines. But you can see it in the book, I think. But I want to move forward and see when we learn about a new thing, we want to know if this thing looks like another thing. What I mean to say now is that what are the morphisms in this category? And what we define now is that this thing is how we define, this way is how we define the morphism between 2 partial actions. So we have a map here, phi here, and phi must respect the domains and image of this every partial action. You have this, which is the contain, and the other thing that is that it respects the image of by the action. And what we have here is that let's before we get confused by this definition, is that if we have this function is going to be called a G equivariant because it moves a partial action inside another partial action. But it does not mean that the 2 partial actions are equivalent. I don't know if you understand me. Because this is a bit misleading, I think, because the word equi means something that is equal, but in fact,
no, equivariance is, let us call it covariance.
Yes.
Very often people use covariance instead of equivariance, so you will not have this idea of equivalence of something.
Yes. This does not mean the equivalence.
No. It is a morphism of dynamical systems.
Exactly. That's
this category in which the actions are only partial. And
yes,
to have an equivalence, isomorph dynamical systems.
Yes. And there, and yes, and then what we do is to move a partial action inside another. But to 2 partial actions to be equivalent now, we need that the inverse function, well, of course, the function must be bijective, and the inverse function must be must satisfy also these 2 conditions. it's not guaranteed at all that the inverse must satisfy these conditions. The main reason here is this condition 1, because as you can see, we can, if we assume the function of phi bijective, we can apply the function in the two sides, and we don't have this condition if we have something like this. An easy example will be taking a group acting, partial acting on a space in two different ways, strictly different ways. So the identity is going to be bijective, and if we move, if these two actions are rather one containing than the other, we can have a morphism which is not isomorphism. For example, if we take the group C in the half plane, we can take the partial action of C in this space by, let's call theta n, which is going to be moving we only need with one, moving two spaces up. And the other action could be mu sub 1, which is going to be moving one space up.
One space would mean 1 centimeter, 1 unit.
Yes, one unit up, 1 unit. Then what we have here is that we can define phi as the identity map in H. And what we can see here is that the domains of this partial action are going to be contained in the other partial action. The other, or no, it's the other way around. These domains are going to be contained in this one. But when we strictly contained, we can just see it right now. For example, how the image of phi 1 of the whole space, because we can see that this is the domain of theta 1 is the whole space. This is going to be the whole space, one 1 centimeter up. So this could be something like this. Why like this? And this one, well, that is mu 1 of H is going to be equal to x y, but y is going to be greater or equal to 2. As we can see now, if we move, we consider this morphism, this going from H to H as well as here, but here we're consider the action mu, and here we're consider the action theta. As we can see, we are satisfying this condition here, and also this condition here trivially. Because phi is the
identity.
Thank you. Yes. Yes.
So in this example, if I understand well, the identity is bijective morphism.
Exactly.
But the inverse, which is once again the identity, is not compatible with the action. It is not covariant.
Exactly.
Okay, so this happens even in simple situations.
Yes.
Who remember what happens in classical dynamical systems? Felipe or
I
Nestor,
don't remember
if you have a bijective covariant action between two dynamical systems, the inverse, which exists because we asked bijectivity, the inverse is automatically covariant or not? If you don't know, we will not spend some time on this. We could solve it.
I don't really know, but I am tempted to think that the answer is yes.
I also think so.
Yeah,
So the difficulty is now because of the domains, because partial actions are too complicated and you will not prove the, you know, this is typical in many categories.
Yes.
If you have a bijective linear map, you know that the inverse is also a linear map. This also happens for in group category, in many other situations. But the inverse of an analytic function is no longer an analytic function. And there are other type of, so there are categories which are full with respect to inversion and other categories which are not full with respect to inversions. It seems, if we believe Felipe's, let's say, intuition or hope, that the classical dynamical systems are stable with respect to inversion. The morphisms are stable, and in this time, in this case, you don't have the property. Well, let us check it, and next time you tell me if the classical case was really better or not. I think it is.
I think also because, excuse me, because a sufficient condition to the inverse to be also equivariant is that we can change this condition to the equal one. If we change it with this one, then we have automatically that the inverse is also equivariant.
Yes, I think so. So I just look at the point 2. The point 1 is automatically satisfied. There is no problem. There are no domain issues. And in the second one, I note phi of x by y, and I write again these things in terms of y, and it is a proof, I guess. And on the other hand, you can see that this isomorphism problem for partial actions is quite exigent. The counterexample of Diego can be generalized a lot. Each time that phi is not dilating something, if it is the identity, then you will need the domains to be the same, to correspond exactly. Yep. You cannot have a domain which is twice as big as the corresponding domain of the first action. If systematically the domains are larger, with the identity, you will not have an isomorphism. It is bijective, it could be covariant, but the inverse will no longer be covariant. So this is already a big difference between classical dynamical systems and partial dynamical systems.
It makes sense because, I think it makes sense that it is actually very exigent, because in the only case that there is the covariance in both directions is that we actually have the same partial dynamical system. Like, it's the same looking somewhat different, but like here, these two systems that Diego presents are clearly not the same. One has somehow a copy inside of the other, but they don't move the space in the same way. So
yes,
it's natural that it's hard to find an equivalent relation between both of them.
It may not be very hard. It depends on the situation, because phi is free not to be the identity. Phi also connect to the domains, let's say. So let me say that very, very rarely the identity succeeds to be an equivalence between two partial dynamical systems. If the domains have the tendency to change shape, the identity does not work. But there could be something different, of course. Just think of a certain dynamical system in Rn and make a dilation by 2 of all the domains and all the mappings. Well, in this case, phi should also dilate things. So it is possible, obviously. If it was not possible, there was not such a definition in the book, I guess. But this is critical. This has to follow what happens with the domains. If not, the inverse could be very bad with a very good direct mapping. Oh, let's go on.
Well, the other thing that we're waiting for now is that we have a groupoid here, which is rather normal now to think about groupoids. And this is a very common groupoid that we can build, where we can only multiply two elements like this, H and W. This is going to be equal to Y, GH, and W, and this is going to be operable. No, operable.
Composable.
No, composable. Thank you. Composable.
Yes.
If x equal to 7, so we are in the same way, or so to speak. This is interesting because, for example, G is in fact, of course, is going to be theta G, which is going to move X to Y, and X is going to be in the domain of theta G. So, for example, if we compute R of theta G, what we're going to get is something like the identity map on the G. So to speak, again. The range map in the groupoid.
The groupoid sense.
Yes, I'm sorry. Yes.
Okay, I agree. So when you write theta G, it already comes with a pair of sets. The first one, which is dg minus 1, the other one, which is dg. So even if you don't write them, this is a triple in a certain sense.
Yes.
As in the definition before, as in the line in which you define the groupoid. Okay, so we agree. Yes. This is a triple, but you don't see the domain and the range because they are understood.
Yes, yes. Yes. That's why I put it a bit far off the equal. It's not the same, but it's the idea. And well, this is a very well-known groupoid, and going forward, now we're getting to. Huh?
Just a moment, Diego. So we hope in the future, because we would like to arrive at C-star algebras, and we already know that each groupoid comes with a C-star algebra. One of our ambitions will be to define C-star algebras also for partial actions of groups. And hopefully, and this is true, the C-star algebras will be isomorphic. So if from a partial action of a group, you construct this groupoid, if you have topology, because without topology, you will not arrive at C-star algebras. So if you have a topology which propagates from the partial action to the groupoid, and then you compute the two C-star algebras, the one we know, the C-star algebra of the groupoid, and the other one that will be invented in the future in a certain chapter, the C-star algebra of the partial dynamical system. Finally, with some effort between the two, there will be a sort of two different points of view on the same C-star algebra.
Yes. Yes. Yes, you could say other moment. Well, moving forward, the other thing that we're missing about dynamical systems global dynamical systems is what are the invariant sets. There's no strange thing here. So the only thing is that a set is going to be invariant if we apply every element of the group in a reasonable way, which is showed here. Then we get inside this set again. Reasonable because, of course, y must could not be inside the domain of this function, so we intersected with the domain of this function, and then we applied the action, the partial action of the group in this space, and we're going to get inside again of this invariant set. These type of sets are going to be very important because now that we know what means to have two partial actions, one inside another, I'm sorry, one equivalent or covariant to another, what we have here, now what we can define is what it means to be, what it means to have a partial action inside another partial action. And invariant sets are going to be very useful to us to define this type of objects. So now that we know what are invariant sets, we can define sub-partial actions. Yes?
Do we have like trivial invariant subsets like in representation theory? For instance, the empty set or the whole space?
Oh yes, of course. I think I'm not just very. I'm not an expert here, but for example, we can take the whole space. Here is.
But if you take y to be equal to the dg inverse, is it true?
No, but this must be by every element of the group.
Yes, so Victor, be careful. You need set y satisfying a certain condition for every g. So you, in this case, for the g that you already fixed, probably you can arrange things easily. But then you change the g, you put an h, and you will lose the.
Yes.
Okay.
So a priori, you are only guaranteed with the fact that the empty set and the whole space are always invariant. And I'm sure that there are situations in which there are no others, and they will be called minimal partial dynamical systems, of course.
So X
and no, minimal, well, you will need a topology because minimal also involves density of something and closures.
Okay.
Anyhow, you are not sure if you arrange things just for a G, it will go wrong for another G prime or H.
Okay.
But what you can do,
on the
for
other
example,
hand, I can give you. Yeah, sorry, I can give you an example. So Diego made all kind of vertical upward shifts on half a plane. So he acted with a one-dimensional group, let's say Z or N, vertically on a two-dimensional space, which is half a plane. Now take half of the half plane, take the part which is to the right, and it is invariant because, well, the boundary between the two is vertical. Just imagine what happened. If you have points x, y in the half plane, and if they are both positive, they will stay both positive after making a vertical shift, a vertical imperfect shift, the shift which cannot be inverted. But it cannot be inverted because of vertical reasons. So this is a simple example in which you have a non-trivial invariant set, and it is honestly invariant. So I guess that you would easily check the invariance condition without difficulty, if I'm not wrong.
I was thinking of only one ray.
And not just this one. There are
Yeah.
an infinity of of quarter of planes which are invariant, because I can shift by 2 centimeters to the right the boundary, and once again I will get a invariant decomposition.
In fact, I was thinking of an example that is just what you said. I mean, here you can also define what is called an orbit. So you can take up an element and take the orbit of this element, and this is going to be invariant here. Well,
yes, but Victor could ask, what happens if each time the orbit is entire space? This can happen. You still don't give an explicit example of decomposable situations. But we have seen, well, the orbits in your first example, in the motivating example, are vertical lines, discrete or continuous, because I did not even understand if you're...
yes, it's just points, I'm sorry.
Okay.
Yes,
okay. So discrete vertical lines are the orbits in this case.
Yes.
Or they are not. No,
yes.
no,
Yes.
let me see. I think they are, but you need to look at the domains of the inverses. And I think that it is okay.
But these lines that start at the bottom of the...
Yes, I agree. But now you would like to apply theta index -3, isn't it? But now the domain of this one is just part of your vertical discrete line. The
yes,
part
but
starting from 3.
this is 3, going to 4, be the...
5, yes. So it is okay. It's really the orbit, this
So actually that example justifies why we don't want the equality, but just the contention in the definition.
We will not have equality in most of the situations. Yes.
Yes.
Because you are right, Nestor. For a classical dynamical system, if I have inclusion, I will have equality. Because I can apply once again all the inverses to the left and they cancel, and you will get the opposite inclusion. This means equality. In our case, you don't get equality in most of the situations. You're right.
And well, as we can see in this example, now that we're stuck here in this example, we can see that here we have a partial action also. Here, instead of taking the whole space, we can now define an action here by the entire this group. We can define also a partial action, which is going to be inherited by the global action or the complete action, for so to speak. And this is going to behave very, very well. In fact, it's not that strange to see that this group acts very well by restricting the global action, which was in the whole half plane. And this is the notion that we need, because this is why we need invariant sets to define what is going to be a sub-partial action. And here we can see, we can consider this as the ray starting at the bottom, the discrete ray. And just the new action is going to be a restriction in this space. And it's not hard at all to prove this. And also, of course, as to see as a substructure, then if we consider the inclusion here, we need to have an equivariant map here. And this is very easy to prove. Also, if you want, I can prove it, but I just got here in this presentation. In fact, this is the last part, so I don't know if you want to prove this or we can discuss a little bit more.
Can I ask a question?
Yes, yes.
Do we have here like the notion of product of partial actions?
The what? I'm sorry?
Product of partial actions.
Ah, product.
Yes.
I don't know. I don't know if
I'm waiting for
I think
Felipe to give us a smile.
they might work, I think.
Try
I
to
am
define
making.
it.
That's try to define. I think that they should work or no?
I think so.
because if we have two actions like theta and mu, we have to change some of the conditions. For example, I think that we need something like
well, Diego, you should ask Victor something more. One group or two groups, because when you are doing products of dynamical systems of a certain type, you have two possibilities: to take two different groups acting on two different spaces, and there the definition is simpler, although it seems that it is more complicated. Or to take a single group and two actions on two spaces, and to put them together. This would be a sort of diagonal version of the product action. And working with Felipe, with groupoids, we discovered that it is still a problem to define the diagonal version, the second one, because there you need, at least for groupoids, you need a sort of matching to put together the two actions, because they were not fully defined. So I am interested if you can, if you still have 10 minutes now, we could try to define first the G1 times G2 action on X1 times X. And I hope that this is, and let's see what happens if the groups are the same. This means what would be the square of an action? Well, I don't know who can write. The person who technically has a possibility to do it. This means,
but I think that you can write also here with the mouse if you are interested.
I can write?
Yes, you can pick. There is something called annotate. And then you can write like this. That's the mouse. That's my mouse. Let's see.
I don't know.
Let's see, two groups. And they act in one set.
No, into different sets.
Into different sets. Because two sets was rather easier. Okay.
And let us put the indices upwards. Up yes. Indices, because as lower indices, you will have the elements of the group.
G2, X2. And this is by theta. And this is by mu.
Should this, does it read well for you? I was writing this like before Mario said that about the...
yes, I can read.
Or it reads well, or does it read reverse?
Don't move it, don't move it. Now I can see it. It seems reasonable and it seems okay, isn't it?
Mm-hmm.
So you have, you take products of domains and products of functions.
Yes. Here you should have theta sub this. Like.
Yes, of course you would need to check the axioms, but it is rather plausible that you will succeed.
The problem I see with that is, I mean, we are using distinct groups.
Yes.
This one seems okay. Well, I tried to imagine the axiom. Let me see. Oof. Anyhow, I have problems with Zoom now because I only see Nestor and I'm no longer able to see the other ones.
Oh.
It's not your fault, I mean. I did something strange.
I have the impression that if we consider these two partial actions and we don't consider any topology, then the problem is kind of just looking at two different actions like separately but at the same time. I kind of have the fear that if we give some kind of topology here and we consider limits, then the limits might not look just as two separate things. Because like in what I wrote, I think we're just like looking at two different moments, two different objects, but at the same time.
Well, I'm not sure. I think that even with a topology, anyhow, you have to decide having topologies on G1, on G2, and then on H1, on X1 and X2. What are the topologies on the product? And you will take the product topologies, obviously, because it's natural choice. And with this one, I think that this will go through. This will be okay. This is what I feel. I'm more afraid of checking the restriction axiom, the fact that composing two elements, G1, G2 with H1, H2, you will, but I still believe that this is okay. But
I think the problem came when we consider the same space here. Instead of, I mean, in the case we want to do something like this, D1 times DG2 and go to and go to one set instead of a product of sets, something like that.
Well, I think that this is still okay. And now thinking of the diagonal situation, the same group acts by two actions, θ1 and θ2, on two spaces, x1 and x2. Once again, it seems that it goes okay. So now my question would be for Felipe. How does this match with our difficulties in the case of groupoids? Because when two groupoids act, there is a matching property. There is, if you remember the mini course given by Diego, there was a function rho going from the space on which you want to act with a groupoid to, it goes surjectively to the unit space of the groupoid. And if you have two such objects, you need a sort of matching to define the diagonal product action. And in our case, it seems that such a difficulty does not appear. But probably this does not appear because when you compute the groupoid associated to partial dynamical systems, this goes the easy way. This goes with an injective function rho or something like this. Well, it was not very clear what I wanted to say. I guess that only Felipe believes me that understands my fears. And
yes,
in addition, I cannot.
I don't remember quite exactly, but I think that the problem was with taking the same element of the groupoid acting on two different points at the same time. I mean, because
Yes.
the problem was exactly with that function, the raw function. And in this case, I was thinking that if one tries to do the same, I mean, you take the same group and try to act like a diagonal action, maybe you have to act, I mean, the domain of the of the domain inside the diagonal action, it should be like the intersection of the domains, I think.
Well, to give a meaning to our fear, to our problem, would mean to do the entire correspondence. This means to write the two groupoids associated to the two partial actions, and then to see if the product of the two groupoids, which we finally define correctly, it is not very difficult, but it needs a certain restriction. If this one corresponds to the product of partial actions, and this needs a quarter of an hour of computation. And only after doing this, I would understand if there is a problem or not. Because if I look at this problem directly in terms of partial actions, it seems that everything goes okay, even if the two groups are equal. Well, I don't know if one of you succeeded to do some computations and to convince himself that everything is okay, please tell us, because I struggled with the system. Now finally I succeeded to see once again the KSS.
I have the impression you might have pressed like the bottom up that only shows like one person, or like the gallery view.
Well, anyhow, now I see the file, Diego's file. I no longer see the faces. But I know
is there a bar over all of us or not? You only see Nestor, right? And over Nestor, there is any bar there?
No, sorry. I no longer see Nestor. I'm very sorry for him. Now I see your PDF file. And to be honest, I'm more happy now because I wanted to see the formula.
You see the full text.
Well, don't mind. I still don't manage this system very well. So do you have an opinion? I think that products can be defined smoothly. And since until next time, I will try to see why the groupoid point of view seems nasty, and how does it fit with the fact that the partial action point of view is not nasty, if it is not, because anyhow one has to check the axioms. So let us leave this for the next time. It is homework, let's say, and it should not be difficult. If it works, this should be done in a quarter of an hour. And finally, let me recall you how rich the theory, how rich in examples the theory is. So take your favorite dynamical system, having something inside. So it should not be a point on which a nasty group is acting, something rather big, and make all the possible non-invariant restrictions. Let's say that something is acting on a sphere, or a group, another group is acting on the plane, or on something more interesting, on a higher dimensional torus, who knows? And then take any subset of the space, anyone, and you will get a partial group action. The trick is that taking an invariant subset no longer ensures you that each of the bijections you had at the beginning, because this is a classical dynamical system, global dynamical system, you have plenty of bijections behaving nicely. Now each of them will no longer be able to act on the entire half space, on the entire subset. But then you arrange things so you take only the points x in the subset such that theta g of x is also in the subset. This could be a drastic restriction. So these are already subsets of the subset. You understand me? You restrict it from x to y, and y is not invariant. At the beginning, on x, you had a global group action. now you try to define things only on Y, but some theta x applied, no, some theta, sorry, what were the, G, sorry, G was the element of the group. So theta G applied to certain elements Y of the subset capital Y no longer stay in Y. This defines you new domains, smaller domains strictly contained in Y. This would be a sort of DG equal to capital Y intersected with the points X, which are sent by G once again into Y. You ask that both the domain and the image by G be subsets of Y. And this could be a smaller subset than Y. And the same for the ranges. And you already obtained a partial dynamical system for any non-invariant or non-invariant set. So
it's
the fact,
similar
yes,
to what it's somehow similar to what Diego says, like to Diego's example from the beginning. Like it comes from like the full grid example, and your Y might be somehow the Diego's half plane, and
sure.
then you find these like the vertical lines are the domains.
Făcut prostii. Nu mai văd, mami, da. Și acum nici nu mai au.
What happened?
No.
Sorry, do you hear me now?
Yes.
For a while, I
Yes.
did not hear you. Well, okay, I wanted just to say that any restriction of a global dynamical system is a partial dynamical system in a very natural way. So if you have 15 nice dynamical systems, you will get probably an infinity of partial dynamical systems starting from these 50 ones. And it is remarkable that what follows in the book is possible. This means in such a generality, with such a freedomness, you still are able to do a theory, to get results, to get classifications, to get later C-star algebras, which have nice properties, and so on and so forth. Just you started with a global system and you do anything you want inside. And then you have a future, you have a theory, it will really work. Applause is enthusiasm. Okay, I was kidding. Well, thank you very much. Let us go on next week, okay?
Yes.